All right. Continuing with part two of the lecture. The next thing is just to compare this a little bit with the heat transfer problem that we have talked about in the past. First thing to note is that for the heat transfer problem, we introduced shape functions for the triangular element and for the quadrilateral element, and the shape functions that are used for the linear elasticity problem are exactly the same. So the definition of the element and the shape functions, which are used to interpolate functions and derivatives, that remains the same. I'm not gonna go into the details, but for example, for the triangular element, you might have linear, quadratic, cubic elements. They just have more nodes, and then you can look up the definition of the shape functions for these different elements. For the tetrahedra elements, we haven't really done anything in 3D, but you should just know that in the same way that there's for triangles, there's some shape functions that are standard. You can also define standard shape functions for different tetrahedra elements. For linear tetrahedra, for quadratic or cubic, you just have more nodes, and then you have the associated shape functions for each node. And that's just something that you can look up. The book, I don't think, has many definitions for tetrahedra. I think it focuses mostly on the 2D shape functions, but there's many other books. For example, this illustration is from the Sankovich and Taylor finite element book, and then I can provide the more details about the reference. But yeah, just all you need to know is that there are some shape functions for different elements, and if you want to use if you wanted to code a particular element, all you will need to do is to look up these shape functions, which are already defined. But in case you don't, all you need to know is that there are different elements: triangles for 2D, tetrahedra for 3D. There's quadrilateral elements for 2D, usually done with these Lagrange polynomials that we have talked about. There's hexahedral elements in 3D. And again, you can find the shape functions. Integration. So that's something that that the weak form entails these integrals, and that we have talked about the definition of the stiffness matrix and the force vectors, and they are basically just integrals. So the stiffness matrix, for example, is integral of B matrix times D times B matrix. And that B matrix has the derivatives of the shape functions with respect to x, y, and z. And to do that integral, you most of the times you cannot do it analytically, or we just take too much trouble to try to do it analytically, so we do it numerically. For example, for quadrilateral elements or hexahedral elements, we use Gauss quadrature, which you have been doing a lot in the past. And from the abacus terminology, and also we have done it in class, that there's different numerical integration schemes, and that if you don't use enough integration points, then you might not capture the correct integral, but it's cheaper. So most of the times, if you use the reduced integration elements, you'll be fine. But in some cases, you might need full integration. And this is something that we did in particular within Abacus. We did this one lab of the shear force at the end of a cantilever beam, and then we tried the different elements. And for example, there we showed how the reduced integration elements had some trouble because they had some deformation, some modes of deformation that didn't take any energy. So by doing the reduced integration, we were basically making it too compliant, making the element too compliant. So that's something just to keep in mind. There's integration rules for triangles and tetrahedra, and there's also full integration or reduced integration. And again, we've covered a lot more of the Gauss quadrature. We haven't really talked about integration on triangles, but it follows sort of the same pattern. You might have, for different degrees of the shape functions from linear to quadratic to cubic, you need more points at which to evaluate in order to calculate the integral, and you have weights associated to those points. There is integration schemes for tetrahedra. There's integration schemes for hexahedra elements. But going back to this question of reduced integration versus full integration, and again, to what we saw in the lab, the Abacus lab that we did, with reduced integration elements, you might have these unstable modes. So there's modes of the formation of the element that carry no energy. And therefore, your elements might deform in this particular way because when you're doing the reduced integration, you're not capturing the energy associated with these deformations. So, for example, these are some common ways in which you might see patterns of the deformation of the mesh that are actually not due to any stress. These are just because they are free energy modes. When can this happen? And then how can you spot when you have this type of instability? You will see some patterns that will let you know that there's something wrong with your solution. So, for example, in this case, again from the Sankovich and Taylor book, if you apply this point force for these quadratic elements with reduced integration, what you'll get is that they will deform in a way that doesn't look physical. And that's just because there's modes of deformation, again, that are not carrying any energy. Also here, there's always some issues with having point forces. So as I said, also point forces lead to singular stress distributions. So that's another thing that you have to be careful about. But if you see this type of patterns of deformation in the mesh, then you should be thinking, oh, this looks like some instability, some oscillation. Maybe there is some zero energy mode in my solution due to the reduced integration. Another type of problems that you might have issue with is incompressibility. And this is because, and I want to bring this up because we have also talked about the idea of convergence. So when you have a mesh for a model, you run the simulation, you get some values, then you refine the mesh, you get new values for your simulation, and maybe they look very, very similar to your first simulation, but they might be a little bit different. So you refine the mesh again, and as you continue to refine the mesh, you should see that the solution stops changing. And this is something that we did, for example, for the plate with a hole. As we refined the mesh, we got closer and closer to the analytical solution, and then at some point, there's basically no change in the solution, even if you refine the mesh. You have done this also numerically by coding in Python the 1D linear solver for the linear elements, and you saw that as you refined the mesh, you got a more accurate response. And then at some point, then like we did for the quadratic element, for the heat transfer problem in 1D, at some point you cannot get any better. You are at machine precision. And then you see that the solution is just not changing. And so that's something that you have to do when you are doing a simulation. You want to check that your mesh is fine enough such that there's no more change in the solution if you refine the mesh. However, in some cases, your solution might converge, but it will converge to the wrong solution. So there's couple of points here. I guess I have many points. So one of the points is that again the solution might converge as you refine the mesh. For example, for nearly incompressible problems, it's not just enough to have finer and finer meshes because your solution will converge, but it will converge to the wrong solution. That's one thing. There's another thing that can happen is shear locking, which we also did in one of the labs, the cantilever beam. We introduced the term of shear locking, and then that can be bypassed with higher degree polynomials and mesh refinement, having enough elements to the thickness. And then I guess this one was the first point, but I am covering last, which is the order of convergence. And what you did for the linear, I think we did it for both heat transfer and the 1D elasticity. So in one dimension, when I asked you to solve the problem with linear elements or with quadratic elements, what you saw is that the solution converged quadratically for the displacements of the temperatures and linearly for the gradients with the linear shape functions. And for the quadratic shape functions, the order of convergence was greater. And you have to be careful because that's not always the case. So the convergence, how fast your solution gets accurate, yes, it depends on the shape functions that you're using, but it also depends on whether or not your problem has singularities. So if you have a problem where you have point loads and you have this singular stress field, then even if you use cubic or quadratic elements, you won't get a higher degree of convergence. And so that's something that you have to keep in mind, that singular loading conditions will harm your convergence. So ideally, you would like to have smooth geometries, not point forces, and that would basically get you the best convergence out of your linear, quadratic, or cubic elements. So that's something to keep in mind. It's not just about mesh refinement, it's also about the regularity of your solution. So how smooth your problem is, whether or not it has singularities. So those three things are three things that you have to be careful when refining the mesh. It's not all about refining the mesh. Again, you have to be careful about the fact that the solution, if it has singularities, even if you refine the mesh, you won't get the desired convergence. Another one is that if you have a problem that is incompressible or nearly incompressible, your solution will converge, but it will not converge to the correct solution. And also that why don't you want to have coarse meshes is because, well, you don't have accurate solutions, and some of the ways in which you don't have accurate solutions is due to things like shear locking, which can be prevented with higher degree polynomials and mesh refinement. For the incompressibility problem in particular, the one thing that I would like to point out is that this is the convergence that you would get as you refine the mesh. So you can see that the element size, so for example, for a material that has Poisson ratio 1/3, so that one is not incompressible, and that one, if you use different elements, you will get convergence. So as you refine the mesh, you can see that the solution that you get, for example, for the deflection of a beam, it gets closer and closer to a value, and then it stops changing. So this is what you would like to see when you are solving a problem. You want to refine the mesh, and then you want to evaluate, for example, the stress at a point and see how it changes, and then eventually it settles down to a value. What happens when you have a material that has Poisson ratio close to 0.5? So this is a nearly incompressible material. If you just use the standard elements that Abacus has, it will look like it is converged. So it won't change. You will refine the mesh and you just won't see any change in the solution. And you might think, oh, my solution is converged. This is the value of the displacement. And in reality, that is not the case. So if you use different elements that are particularly designed for nearly incompressible problems, then you see that your solution actually converges to the correct value. So again, just to keep in mind, if you have nearly incompressible problems, do not use the standard problems. There's a type of element, do not use the standard elements. There's a type of element in Abacus that you want to use. For 3D stress analysis, the theory is very, very similar to what we have done in 2D. You just have a three-dimensional stress. The gradient operation is just a bigger matrix. So I'm not gonna go into the details here. I guess the only thing that I would like to point out is that the equations are the same when you look at them in vector form, but you have now an extra degree of freedom. So then all the matrices will get a little bit bigger, but the idea is pretty much the same. So I would say there's no really need to worry about in terms of the theory behind it. It's pretty much the same between 2D and 3D. Yeah, I'm gonna skip this. I think that's it. Yeah, so that concludes this lecture.